Quantum Quandaries and Cosmic Curiosities, a discussion with Dr. Cooper and Dr. Newton. Ladies and gentlemen, welcome to the most anticipated event of the year, Quantum Quandaries and Cosmic Curiosities. I'm Max Humer, your host for tonight. Get ready for a journey through the cosmos, filled with twists, turns, and a sprinkle of comedy. Please welcome our esteemed guests, Dr. Alice Cooper and Dr. Bob Newton. Dr. Cooper, Dr. Newton, it's a pleasure to have you here. Let's start with some introductions. Dr. Cooper, tell us a bit about yourself.
Thank you, Max. I'm Alice Cooper, a theoretical physicist specializing in quantum mechanics and string theory. My research focuses on the fundamental nature of reality and the possible existence of parallel universes.
Fascinating. And Dr. Newton?
Thanks, Max. I'm Bob Newton, an astrophysicist dedicated to understanding black holes, dark matter, and the large-scale structure of the universe. I also dabble in cosmology, trying to decipher the origins and fate of the cosmos.
Wow, we've got the Quantum Queen and the Cosmic King here tonight. Let's dive right in. Dr. Cooper, can you explain quantum mechanics in a way that won't make our brains explode?
I'll do my best, Max. Quantum mechanics is the branch of physics that deals with the behavior of particles at the atomic and subatomic levels. It's a world where particles can exist in multiple states at once, known as superposition, and where they can be entangled, meaning the state of one particle instantly affects another, no matter the distance between them.
So, particles are like teenagers. They're in multiple moods at once and always affecting each other from a distance. Dr. Newton, how does this quantum weirdness fit into the cosmos?
Great analogy, Max. Quantum mechanics is essential for understanding the fundamental forces and particles that make up the universe. It's crucial for explaining phenomena like black holes and the behavior of matter under extreme conditions. In cosmology, we use quantum mechanics to explore the early moments of the universe, right after the Big Bang.
Speaking of the Big Bang, I always thought it sounded like a great name for a rock band. But seriously, Dr. Newton, can you break down what happened in those first few moments after the Big Bang?
Absolutely. The Big Bang marks the beginning of our universe, occurring about 13.8 billion years ago. Initially, the universe was an incredibly hot, dense point. In the first fractions of a second, it underwent rapid expansion, known as inflation. During this time, fundamental particles like quarks and gluons formed, eventually cooling down to form protons, neutrons, and electrons. This led to the creation of atoms and eventually stars and galaxies.
So from a hot, dense point to a universe filled with stars, talk about a cosmic glow-up. Dr. Cooper, how does string theory fit into all this?
String theory is an attempt to unify all fundamental forces of nature, including gravity, into a single theoretical framework. It proposes that the basic building blocks of the universe are not point particles, but tiny, vibrating strings. These strings can vibrate at different frequencies, giving rise to the various particles and forces we observe.
Tiny vibrating strings? Sounds like the universe is one giant cosmic guitar. What are the implications if string theory is proven correct?
If string theory is correct, it could provide a unified description of all physical phenomena, potentially solving many of the mysteries that currently perplex physicists, such as the nature of dark matter and the behavior of black holes at a quantum level. It might also reveal the existence of additional dimensions beyond the familiar 3 dimensions of space and 1 of time.
Extra dimensions? That's like finding out your house has secret rooms you never knew about. Dr. Newton, how does dark matter fit into this grand picture?
Dark matter is one of the biggest mysteries in astrophysics. It's a form of matter that doesn't emit, absorb, or reflect light, making it invisible to current instruments. However, we can infer its presence from its gravitational effects on visible matter, such as stars and galaxies. It's thought to make up about 27% of the universe's mass energy content.
So, dark matter is like the shy kid at a party. You know they're there, but they don't make a scene. What's the latest in dark matter research?
Researchers are exploring several approaches to detect dark matter directly, including underground detectors designed to catch rare interactions between dark matter particles and ordinary matter. There are also efforts to create dark matter in particle accelerators like the Large Hadron Collider by smashing protons together at high energies.
Sounds like the ultimate cosmic hide-and-seek game. Dr. Cooper, back to quantum mechanics. What's the deal with Schrödinger's cat?
Schrödinger's cat is a thought experiment proposed by Erwin Schrödinger to illustrate the paradoxes of quantum mechanics. It imagines a cat placed in a sealed box with a radioactive atom, a Geiger counter, and a vial of poison. If the Geiger counter detects radiation, the vial is broken, killing the cat. According to quantum mechanics, until we open the box and observe the cat, it's in a superposition of being both alive and dead simultaneously.
So the cat is both napping and not napping until you check. Sounds like my weekends. What's the real takeaway from this experiment?
The real takeaway is the concept of superposition and the role of observation in quantum mechanics. It highlights the strange and counterintuitive nature of quantum states, where particles can exist in multiple states at once until measured.
Speaking of counterintuitive, Dr. Newton, can you explain black holes without giving us an existential crisis?
I'll try, Max. A black hole is a region of space-time where gravity is so strong that nothing, not even light, can escape its pull. They form when massive stars collapse under their own gravity at the end of their life cycles. The boundary around a black hole, beyond which nothing can escape, is called the event horizon.
So, black holes are like cosmic vacuum cleaners with no off switch. What's inside a black hole?
Inside a black hole, all the mass is thought to be concentrated at a single point, called a singularity, where density becomes infinite and the laws of physics as we know them break down. The surrounding space is warped in such a way that time and space switch roles, creating an inescapable trap.
Infinite density and warped space. Sounds like a sci-fi movie. Dr. Cooper, any theories on what happens if you fall into a black hole?
If you were to fall into a black hole, you'd experience what's known as spaghettification. The intense gravitational gradient would stretch you lengthwise and compress you from side to side, effectively turning you into a long, thin strand. Once you cross the event horizon, your fate is sealed, and you'd eventually reach the singularity.
Spaghettification? That's one pasta dish I don't want to try. Let's lighten things up a bit. How about some rapid-fire questions? Ready?
Ready.
Dr. Cooper, what's your favorite subatomic particle?
The photon. It's the particle of light and the force carrier of electromagnetism.
Dr. Newton, favorite celestial object?
The Andromeda Galaxy. It's our closest galactic neighbor and offers a glimpse into the future collision with our Milky Way.
Dr. Cooper, quantum entanglement. Spooky or spectacular?
Spectacular! It's a profound demonstration of the interconnectedness of the universe at a fundamental level.
Dr. Newton, if you could travel to any place in the universe, where would it be?
The center of the Milky Way, near the supermassive black hole Sagittarius A. It's a region of intense interest and mystery.
All right. Final question for both. What's the most exciting thing in your field right now?
The ongoing efforts to develop a quantum computer. It has the potential to revolutionize computing by performing complex calculations exponentially faster than classical computers.
The James Webb Space Telescope. It's set to transform our understanding of the universe with its advanced infrared capabilities, allowing us to peer deeper into space and time than ever before.
Amazing. We've covered so much ground tonight, from the tiniest particles to the vast expanses of space. Thank you, Dr. Cooper and Dr. Newton, for sharing your knowledge and humor with us.
Thank you, Max. It's been a pleasure.
Yes, thank you, Max. This was a lot of fun.
And thank you, audience, for joining us on this cosmic journey. Remember, the universe is a strange and wonderful place, so keep exploring, questioning, and, of course, laughing. Good night.